discuss about antenna arrays. So, what are antenna arrays? Till now we discussed about just a single antenna. So, whenever we require more gain or more directivity, that single antenna may not provide that more gain or the gain what we require or the directivity what we require. For that, to enhance the directivity or to enhance the gain, what we do is we will club a similar type of antennas, that such type of arrangement is called as array. That we will arrange all those antennas in a particular fashion. So, that particular fashion will gives you the resultant radiation pattern. That resultant radiation pattern will have more gain and more directivity as per the requirement of our user. So, that array may provide some more gain or more radiation as per the user requirement. Now, what are basic configurations or different configurations of array? That arrangement of elements, the element is nothing but a simple linear antenna or whatever it may be the antenna, we will call that one as an element. That we are not bothering about, or we don't bother about the dimensions of that antenna, simply we will consider that one as a point element or the simple point source, right? Because the radiation pattern what we are considering is very far away from the antenna, the dimensions of antenna will not get come into the picture. So, here clearly remember that we are considering every antenna as a simple element, that I will call that one as an element, right? So, the elements will be arranged as a grid, this is called as a grid array. All the elements will be arranged as a linear fashion, this is called as a linear array. On a straight line they will be arranged, on a circle they will be arranged, that is called as a circular array, or a rectangular fashion, that is called as a rectangular array. Like that, purely depend upon the shape what we are arranging, the array will be called. Now, what is the resultant radiation pattern? What are the parameters which affects the resultant radiation pattern? The resultant radiation pattern of our array will be affected by majorly 5 parameters. So, the first one is the relative displacement of the antenna, the relative displacement between the elements. So, what is the displacement between two elements, that is what is the distance between two elements, that will decide the resultant radiation pattern. And then how we are arranging the elements. So, what is the basic configuration of the elements? This is also one of the important parameters which describes our resultant radiation pattern. And then what is the amplitude we are feeding to the antennas, that let us consider as an example. If you take a 4 element array, this is one element, a second element, third element and fourth element. Element means antennas. That this is a linear array, that what I can say, that for this linear array, what is the amplitude you are applying to each and every individual element or antenna, that also describes the resultant radiation pattern. And what is the phase you are applying here, that is the amplitude, and what is the phase you are applying here, that also describes the resultant radiation pattern. And finally, what is the radiation pattern of individual element, this also describes our radiation pattern. So, the resultant radiation pattern of any array once again will be decided purely based on 5 parameters. So, how they are configured, a linear array, circular array, rectangular array, that's a different array will give you different radiation patterns. The second one, what is the amplitude of each and every individual element, what is the phase of individual element, what is the distance between elements. So, if you are varying this distance also, the radiation pattern will be varied. So, what is the distance between the successive elements, and finally what is the radiation pattern of individual element. Just these are the parameters which decides the radiation pattern of our resultant radiation pattern of our array. Now, what I do is I will go for a general configuration that is called as linear array. So, for our analysis purpose, a linear array will be there. I will go for a linear array with n elements, that n antennas with some general distance, and I will go for the resultant radiation pattern, and we will analyze what is the maximum radiation pattern direction, what is the minimum radiation pattern direction, and depend upon that one how the array will be called. Prior to that, what I do is just I will give you 2 major arrays, they are called as broadside array and end fire array. So, what is broadside array and what is end fire array and what is collinear array? As the third one is a minor category, that is also I will discuss, that is called as a collinear array. Now, I will give these 3. Broadside array, what is broadside array? This is in short called as BSA, broadside array. BSA stands for broadside array. In the examination also they will give you as BSA, and another one is EFA, end fire array. Broadside array is nothing but an array which has radiation pattern perpendicular to the axis. that we have elements, they are aligned on an axis. This is simply a linear array like this. That this is one of the elements, second element, third element, like that n elements will be there, all they are on a single axis. This is the axis of our array. That simply remember the word that axis of our array or array axis. For that array axis, the radiation pattern is always perpendicular. This is the radiation pattern that what you can observe for this particular array. Then this is said to be the broadside array. And clearly imagine, so what we are observing? We are observing the radiation, we are observing the power, we are observing the field. That power or the field is always perpendicular to the array axis. Then simply it is set up the broadside array. This is one of the major categories and which will be widely used in our day-to-day applications. Similarly, the second category, this is the first category. The second category is EFA. This EFA stands for end fire array. End fire array. That end fire array is also applicable for a linear type of array, that n elements will be taken here, that n elements I am considering, and this is called as the array axis. For the array axis, the radiation pattern is parallel. That the radiation pattern will be parallel to the array axis, that is along the array axis. Suppose if you are considering this as the array axis, then the radiation pattern is also along this array axis. Then it is said to be end fire array. So Yagi-Uda array, that's the antenna which is useful for TV reception, is one of the examples for this end fire array. And the third one is collinear array. That collinear array means all the elements will be placed like this. That this is the axis of the element and this is the axis of another element, and these two are parallel. They are on axis of the array. That here clearly the axis of the element as well as the axis of the array will be on same line. Then it is said to be a collinear array. Like this, these three are the three categories of arrays. Now depend upon the conditions, these will be decided. Sometimes an array can be acts as a broadside array. Sometimes the same array can be acts as end fire array. That this will be decided purely depend upon few conditions. Now what we do is we will learn what are those conditions to get a broadside array or to get an end fire array. For that what we do is we will start our analysis with n element linear isotropic sources. That an array is formed with an isotropic sources of n elements. Now what I do is just I will derive the resultant electric field intensity. If we are considering n isotropic sources which are a part of a distance d, and what will be the resultant electric field intensity because of that particular array if it is linear, that what I am going to derive. Just you observe the steps are very easy. Now let us consider n elements are there on an axis. This is the array axis. On the array axis I will consider n elements. This is the first element. Distance between the first and second elements is d, and similarly this is the third element. The distance between these two is d. That all the elements are considered on an axis and the distance between all the elements is d successively. And this is an arrangement that what I have. So this is first element, second element, that's the third antenna. Like this is nth antenna. Because of these n antennas, I require the electric field intensity in far field region. Far field region means the region which is very far away from the antenna array. That somewhere at point P, I am going to calculate the electric field intensity, the total electric field intensity or the resultant electric field intensity, right? The resultant electric field intensity is the vector summation of the individual electric field intensities. So here clearly what you are supposed to remember is the resultant electric field intensity at point P is the vectors addition of all these individual electric field intensities. So what I do is at point P, I will consider the individual electric field intensities and I will add them. So let us consider the electric field intensity at point P. Because of source 1 is E1, because of source 1 it is E1, because of source 2 E2, because of source 3 E3, all they will be added at some point P. This point P is very far away from the antenna array. Since this point P is very far away from the antenna array, I will consider all these lines as parallel lines. So they are not exactly parallel, they are approximately parallel, and assume that all they are making an angle of theta, so with this array axis. So with the array axis, they are making an angle of theta. This is theta, this is also theta, this is also theta, and finally this is also theta. And what is the electric field intensity of our final element? En. Now, because of all these electric field intensities, the total electric field intensity will appear at point P, that ET stands for the total electric field intensity. The vector summation of E1, E2, E3 up to En. So what I have to do is just I have to obtain the electric field intensities because of the first one, second one, third one, and the final one. Just add all those electric field intensities. Now for that, what I do is just I will imagine that the electric field intensity of the first one will have 0 phase. That I will consider that one as the reference, right? So let us take the first one will have the electric field intensity E0 with 0 phase. That E0 J0, this J0 corresponds to the phase of this particular electric field intensity, right? Now with respect to the first one, the second one will have definitely some phase difference. So assume that there is an initial phase difference for the second one. So what is the initial phase difference for the second one? I will assume that the initial phase difference as alpha. So the initial phase difference, that what I am applying initially is alpha. And apart from this alpha, if you observe these two paths, there is some path difference. So this path and this path, these two are two parallel paths, right? Since these two are two parallel paths, this is little bit lagging when compared with the second element. While there is lagging with the second element, there is some path difference between these two. This is the path difference. How to calculate that path difference? Just go to your trigonometry and apply. Since this angle is theta, the path difference is d cos theta. Whenever there is path difference, definitely there will be some phase difference. Now what is the relation between the path difference and phase difference? Phase difference is equals to 2 pi by lambda into path difference, or beta into path difference. So here, because of this path difference, you will have phase difference, right? That phase difference I will consider as psi. The two terms that what I wrote in brackets are the phase differences. Clearly remember that point. This is the initial phase difference that what I am inducing, and this is the phase difference that is appeared because of the path difference. So what is the total phase difference? The total phase difference is the addition of these two, right? Now what I do is this. I will consider this one as suffix p. It represents that it is because of the path difference. So the total phase difference psi is equals to psi p plus alpha. That is, this psi p is nothing but the phase difference because of the path difference, and this alpha is the phase difference which what I am inducing initially, right? Now what is psi p? Psi p is already given as 2 pi by lambda into our path difference d cos theta plus alpha. 2 pi by lambda d cos theta plus alpha. This can be taken as just beta d cos theta plus alpha. This is our total phase difference between the first element and second element. I am not taking the remaining all elements, just between the first element and second element. The total phase difference is a summation of the phase difference which what I am inducing initially, and the phase difference which appears because of the path difference. Now how you can write down the equation of our second electric field intensity, that is the electric field intensity because of the second element? You can write down that one as E naught e power j psi. So this is the first electric field intensity E1, this is the second electric field intensity E2. That clearly the phase difference between these two is psi. This phase difference is the phase difference because of induced one, the phase difference because of the path difference. Similarly, how we can write down the equation of our third element? The third element equation can be written as E3 is equals to, the magnitude is same, that what I am assuming, E3 into e power j. So what is the total phase difference up to the third one? The phase difference between the 1 and 2 is psi, and the phase difference between 2 and 3 is psi. So the total phase difference between 1 and 3 is psi plus psi, 2 psi. So the phase difference between the first element and third element is 2 psi. This is the thing that what I can write. Similarly, for the fourth one, what you can write is E4 is equals to E naught e power j 3 psi, and the final one will have the electric field intensity equation En. that is the electric field intensity for the nth element is equals to E naught e power j n minus 1 psi. Now we have the electric field intensities of the individual elements. All those individual elements will have their own electric field intensity. The first one is just E naught with 0 phase. The second one E naught with j psi, E naught e power j 2 psi. Like that all the electric field intensities are available now. What we have to do is just add them. If we are adding those electric field intensities, then that will be the total or the resultant electric field intensity at point P because of this array. So what I do is just I will add all those electric field intensities now. So the total electric field intensity E T is equals to, the first one is E naught, the second one is E naught e power j psi, and the third one is E naught e power j 2 psi, and so on up to E naught e power j n minus 1 psi. Just what I am doing is I am getting the total electric field intensity. This is a summation of all the electric field intensity which are presenting in that particular array. Now what I do is just I will simplify this equation. For that, multiply with e power j psi on both sides. For this equation, let us consider this as equation 1. Just to multiply equation 1 with e power j psi on both sides. Then what you will get here is e power j psi into et is equals to E naught e power j psi plus E naught e power j 2 psi plus E naught e power j 3 psi plus E naught e power j n psi. I am multiplying that one with e power j psi on both sides. Now subtract equation 1 from equation 2. Just you subtract equation 1 from equation 2. Then what you will get here is Et is common e power j psi minus 1, which is equals to, on the right hand side, this term will be cancelled, this term will be cancelled, and the corresponding all terms will be cancelled. So the term which is left is E naught e power j n psi minus 1. So this is the term which is left for us on the right hand side. Now let us simplify this one. For that, Et is equals to E naught, a simple mathematical manipulation that what I am doing here. Observe, e power j n psi by 2 minus e power minus j n psi by 2 multiplied with e power j n psi by 2 divided by that. If you are multiplying this one, then you will get the same term. In the denominator, what you have is e power j psi minus 1, right? That e power j psi minus 1 can be written as e power j psi by 2 minus e power minus j psi by 2 multiplied with e power j psi by 2. This is the term that what I am considering. This is in the form of e power j theta minus e power minus j theta. This is also in the form of e power j theta minus e power minus j theta. What you will get is here 2j cos sin theta, here also 2j sin theta, and this is the term which can be simplified like this, which is equals to, directly I am writing the equation of Et. So E naught, here it is 2 will be cancelled, jj will be cancelled, the sin term left for us. So sin n psi by 2 divided by, here also it is sin psi by 2 multiplied with, what about this one, e power j n psi by 2 minus psi by 2, so n minus 1 psi by 2. So this is the equation of total electric field intensity because of our n element array. So all the anisotropic sources are arranged as a linear one, and initially we are applying the same amplitude to them, and there is some initial phase difference of alpha. Because of the path reference, there is some other phase difference, they will be added. The total phase difference is psi. After that one, we will get the total electric field intensity as E naught sin n psi by 2 by sin psi by 2 e power j n minus 1 psi by 2. Now this will describe, so what is the radiation pattern structure? So what is the maximum direction for the radiation pattern? What is the minimum direction for the radiation pattern? Minimum direction means the null will be there, zero radiation pattern. So now by analyzing this equation, you will get all those things. So my intention is to get analysis for this particular equation under different conditions. So what are different conditions you may have? You may have many number of elements. You may take only 2 elements, substitute n is equals to 2. or you may take 4 elements, substitute n is equals to 4, or you can take infinite elements, substitute n is equals to infinite. And initial phase difference I am not applying anything, that is alpha is equals to 0, that what you can consider. At the initial phase difference I am applying some pi, that alpha is equals to pi, you can substitute. Like that different conditions will be there, and so using all those conditions you can obtain the resultant radiation pattern. So with the help of that resultant radiation pattern you can describe the condition for different arrays. What is the condition for broadside array? What is the condition for end-fire array? You can describe that one. So what I do is I will consider this equation and I will analyze this equation for different cases. Now consider the magnitude of this particular equation. So my intention is to get the radiation pattern. To draw the radiation pattern, the magnitude is enough. So if you are considering the magnitude, what is the term we will get? The magnitude of Et is equals to this term, the magnitude of this term becomes 1. So simply it is E naught sin n psi by 2 divided by sin psi by 2. Now the radiation pattern is purely depend upon which parameter? The radiation pattern is purely depend upon this parameter, that is sin n psi by 2 divided by sin psi by 2. So by varying number of elements, by varying the distance between them, by varying the initial phase difference, you are varying this term only. The variation in this term will describes you the radiation pattern, resultant radiation pattern of our array. That's why this particular factor is very important. That factor is called as array factor. That in short this is called as AF. That most of the times they will give you as AF only. The array factor, that is nothing but the magnitude of this particular term, sin n psi by 2 divided by sin psi by 2. The magnitude of this particular term will describes the type of radiation and the direction of radiation. That's why this is described as array factor. Now with the analysis of this array factor, you will get the radiation pattern for different cases. Now what I do is I will consider a simple case. So what is that case? Only 2 element array I will consider. In my array only 2 elements are there, that is substitute n is equals to 2, and the distance between those 2 elements is lambda by 2, and the initial phase difference is 0, and I am applying same magnitude or the amplitude to 2 elements. Once again recollect what are the conditions that what I am describing, that I will consider a 2 element array, and for the 2 element array the distance between the elements is lambda by 2 and the magnitude is same and phase is also same, that is the initial phase difference is 0, right? With these conditions I will go with the analysis. Now observe the number of elements are 2, distance between the elements is lambda by 2 and alpha equals to 0 I am considering. Now modify all the equations that what we have. Just what I do is I will consider only array factor. That array factor is enough for us because the E naught is obviously constant. That array factor is enough for us. Consider the array factor. Array factor is equals to sin n psi by 2 divided by sin psi by 2. Now I have to analyze this array factor for the radiation pattern. Before going to the analysis, what I do is I will modify these terms. For the modification of these terms, I will use these conditions. That just imagine how this particular array is. Only 2 element array I am considering, that the distance between these 2 elements is lambda by 2 and I am applying E naught here, E naught here also. That E naught and E naught means same magnitude and same phase. There is no phase difference. That's why I will consider alpha is equals to 0. Now modify your psi. So what is psi? Psi is equals to, what is the basic equation? Psi is equals to beta cos theta plus alpha. That is the basic equation that what we have at the time of derivation. So which is equals to beta. Beta is 2 pi by lambda. What is d? D is nothing but the distance between the 2 elements, which is equals to lambda by 2 cos theta plus 0, which is equals to 2 will be cancelled, lambda will be cancelled. Simply it is pi cos theta. So instead of psi, what you are supposed to substitute is pi cos theta. Instead of n, what you are supposed to is substitute is 2. Number of elements are 2. So the equation of array factor or simply the array factor will be modified as sin 2. Instead of psi I am writing pi cos theta divided by 2. So n psi by 2 pi cos theta by 2 divided by sin psi by 2. Psi is pi cos theta by 2. So this is the equation which is modified for this specific case. Now simply array factor is equals to what you can write, sin 2 will be cancelled, pi cos theta divided by sin pi by 2 cos theta. Now if you want to get the radiation pattern, or if you want to draw the radiation pattern, substitute different values of theta and draw the radiation pattern. So take on x-axis take theta, substitute different values of theta and draw the radiation pattern. Obviously you will get the radiation pattern for this particular case, but it is not possible for us to substitute all the values of theta and substitute. Instead what we do is we will try to get the maximum direction and minimum direction. So in which direction you will get the maximum radiation, in which direction you will get the minimum radiation, that what we will analyze for this particular equation. So just I will consider this equation, I will go for the maximum and minimum directions. So take this equation. Now what is the direction of maximum? What I want is the maximum direction. For the maximum, just you observe when you will get the maximum value for this particular term. This term is maximum if the denominator is minimum, right? So what is the minimum value of our denominator? The minimum value of our denominator is 0, since it is a sinusoidal function. If it is 0, then you will get the maximum value for this array factor, right? So the direction of maximum can be obtained by making our denominator is equals to 0. So make it is equals to 0. That what I am considering here. Sin pi by 2 cos, here I will write this theta as theta max, as we are observing the maximum direction. So sin pi by 2 cos theta max is equals to 0. That what I am considering, right? Now get the solution for this one. That pi by 2 cos theta max is equals to, from 0 to 360, whenever we are drawing our radiation pattern, the angles will be taken from 0 to 360 only. So between 0 and 360, what are different values? You may get 0 for this sinusoidal function, you may get 0 or plus or minus pi. For plus pi or minus pi, you will get, if you substitute plus pi or minus pi here, you definitely will get 0. Now analyze for all these values. This pi by 2 cos theta max is equals to 0 corresponds to cos theta max is equals to 0, or if it is equals to plus or minus pi, then cos theta max is equals to plus or minus 2. Just to simplify this one, pi by 2 cos theta max is equals to plus or minus pi, then cos theta max is equals to plus or minus 2. Cos theta max of plus or minus 2 is always not possible. This is not existing case. So just you observe this cos theta max is equals to 0 and get the solution for this one. So what are different values? You may get this theta max is equals to cos theta max is equals to 0. Obviously only two values are there. They are theta max is equals to 90 degrees or theta max is equals to 270 degrees. So if you substitute pi by 2 here, you will get 0. If you substitute 3 pi by 2 here, you will get 0. So obviously what you can say is the radiation intensity has its maximum value in these two directions only, as this is not existing one. So in the 90 degrees direction, the maximum radiation will be there. In the 270 degrees direction also, the maximum radiation will be there. Just to keep them in mind, because we are supposed to calculate the minimum directions also. After that one, we will try to draw the radiation pattern, right? Now my intention is to get the minimum radiation pattern. Now what is the minimum value of our array factor? The minimum value of our array factor is 0. So whenever the numerator is equals to 0, obviously you will get the magnitude of our array factor will be 0. So for minimum radiation pattern direction, make our numerator to 0. So consider our numerator. What is that one? Sin pi cos, instead of theta I will write minimum, because we are calculating the direction for minimum radiation pattern. So this theta will be written as theta minimum. So sin pi cos theta minimum is equals to 0. Now once again analyze for this particular sinusoidal function. Then you will get pi cos theta min is equals to 0, or pi cos theta min is equals to plus or minus pi. So if you substitute 0 here, you will get 0. If you substitute plus or minus pi, then also you will get 0. Now from this one, cos theta min is equals to 0. Cos theta min is equals to 0 means, what is theta minimum? Theta minimum is equals to pi by 2 or 3 pi by 2. So in the direction of pi by 2, you may get minimum. In the direction of 3 pi by 2 also, you may get minimum. But this is conflict to the previous one. The maximum direction is also the same one, pi by 2 or 3 pi by 2. right? The minimum direction is also same one, pi by 2 or 3 pi by 2. So here what you are supposed to do is you are supposed to neglect this case, and this is not existing one. Then go to the second one. Then from this one what you will get here, cos theta min is equals to plus or minus 1. So cos theta min is equals to plus or minus 1 corresponds to what is theta min? Theta minimum is equals to plus or minus pi or 0. So in the direction of pi or 0, you will get the minimum value. Minimum value of the radiation pattern means null. There will be no radiation pattern, 0 radiation pattern will be there. So these are the values what you are supposed to consider for theta minimum. And just recollect what is the maximum direction again. The maximum direction is 90 degrees and 270 degrees. What is the minimum direction? 0 degrees and pi degrees. So if you are trying to draw the radiation pattern with these values, just you will get an idea how the radiation pattern will be. For that, what you do is just you consider along the array axis theta is equals to 0. That we are considering a 2 element array, that along the axis of that array consider theta is equals to 0 and move as a 90 degrees, 180 degrees, 270 degrees as per your requirement, and try to draw the radiation pattern. Now I will draw that radiation pattern. Observe. To draw that radiation pattern, as I said, consider along the axis of array theta is equals to 0, and somewhere here theta is equals to 90 degrees, and here it is theta is equals to 270 degrees, and here it is theta is pi, minus pi or plus pi, whatever it may be, you can consider as per your requirement, right? Now this is one of the elements that what we have. This is the second element. This is our array axis, right? Now in which direction you are getting the maximum? The maximum radiation pattern is appearing in the direction of 90 degrees and 270 degrees. That is, the maximum radiation pattern will be like this. That is in the direction of 90 degrees and in the direction of 270 degrees. So the radiation pattern is maximum here, the radiation pattern is maximum here. And what is the direction of minimum? The direction of minimum is 0 degrees and 180 degrees. So simply this is a very simple one, that how you can draw the radiation pattern, that by analysis of our effective or the resultant electric field intensity which is generated by the array. That analyze that one. So when you will get maximum, in which direction you will get maximum, in which direction you will get minimum. Now observe this one. For the array axis, how the radiation intensity or the radiation pattern? The radiation pattern is perpendicular to the array axis. Whenever the radiation pattern is perpendicular to the array axis, what is the type of array we have? The type of array what we have is broadside array. So that's why this particular array is said to be a broadside array. To obtain this broadside array, what we did initially, we consider the same amplitude for the elements and 0 phase difference between the elements. These are the conditions what you are supposed to remember for generation of broadside array. Once again I will write here that E naught, that what I am substituting this for these two elements, that the same amplitude you are supposed to apply. And what is the distance between them? The distance between the elements is lambda by 2. And what is the initial phase difference? The initial phase difference I am applying is just 0. So with these conditions you can generate a broadside array. That for clearly it's you may be asked a question like this. For broadside array, what is the initial phase difference between the two elements? 0 degrees, 90 degrees, 180 degrees, 270 degrees. Immediately how to say that there will be no phase difference between the elements for broadside array initially. That 0 degrees is the answer. Like that, just you remember this condition, then easily you can generate this broadside array. Now we will go for the second case, that what I do is I will induce the initial phase difference. If I am inducing a pi plus or minus pi phase difference, what happens to it? Go for that. Here what I am doing is, the conditions, the remaining conditions are same. I am considering only two elements. The distance between the elements is lambda by 2, and the initial phase difference I am inducing as plus or minus pi. In the previous case it is 0, now it is plus or minus pi. The analysis is same, but equations will be varied. For that, what I have to do is once again consider the array factor. Array factor is equals to sine n psi by 2 divided by sine psi by 2. Here the psi equation will be modified. Psi is equals to, what is beta here? Beta is 2 pi by lambda, and d, what is d here? Lambda by 2 cos theta. Here it is, instead of alpha I am writing plus or minus pi. So this is the value of psi now. So simply what you will get here is this lambda will be cancelled, this beta 2 will be cancelled. Simply it is pi cos theta plus or minus pi. So whenever you have this psi, just you substitute that pi cos theta plus or minus pi. So what is the modification you are supposed to do for our array factor? Array factor is sine. How many elements will be there? N is equals to 2. 2 will be cancelled. Psi is pi cos theta plus or minus pi divided by sine pi cos theta plus or minus pi divided by 2. Now this is the array factor what we are supposed to analyze. The maximum radiation pattern, take this array factor, analyze that one. For the minimum radiation direction, take this one, analyze this. So now what I do is just I will analyze this equation. So remember this equation, go for the analysis. Now I will get the maximum direction. So the principle is same, that for the maximum what you are supposed to do is just you make our denominator to 0. So maximum, that the maximum direction, take our denominator sine pi cos theta plus or minus pi divided by 2 and make it equals to 0. If you are making this equals to 0, you make a different values, just obtain all those values, that pi cos theta plus or minus pi divided by 2 which is equals to 0, or pi cos theta plus or minus pi divided by 2 which is equals to plus or minus pi. So if you substitute 0 here, you will get 0. If you substitute plus or minus pi also, you will get 0. Now go to the first one, that pi cos, here instead of theta what I do is just I will write this one as theta max, as we are observing this one for maximum value, theta max. Pi cos theta max plus or minus pi is equals to 0, then pi cos theta max is equals to minus r plus pi. Just you go to this side, then it becomes minus r plus pi. Cos theta max is equals to minus r plus 1. So when you will get minus r plus 1, if you substitute theta max is equals to 0 or pi, you will get minus r plus 1. Therefore theta max is equals to plus or minus pi, or you can write this one as 0 or pi, no problem, whatever maybe you can write, that will be the correct. And go to the second case. In the second case what you have here, pi cos, here also I will have done this one as theta max plus or minus pi is equals to plus or minus 2 pi, and get simplified one of this, that is cos theta max is equals to this plus or minus go to the right hand side, that will becomes minus r plus 2 pi minus pi, that's only pi will be there, pi will be cancelled. Once again you will get plus or minus 1. Cos theta max is equals to plus or minus 1, cos theta max is equals to minus r plus 1, both are same. So here also theta max is equals to, what you will get is plus or minus pi. So clearly the maximum radiation intensity or the maximum radiation pattern will be in the direction of plus or minus pi, or in the direction of 0 and in the direction of pi. Remember that. Now I will go for the minimum direction. For the minimum direction, what you are supposed to do? You are supposed to make your numerator to 0. So for minimum direction, take numerator. What is our numerator? Sin pi cos theta. Here I will write down this one as theta minimum plus or minus pi is equals to 0. Now this entire term will be simplified or obtained as pi cos theta minimum plus or minus pi is equals to 0, or pi cos theta minimum plus or minus pi is equals to plus or minus pi. That what you have. So if you substitute 0 here, you will get 0, plus or minus pi also you will get 0, right? After simplification, what you will get here, cos theta minimum is equals to this plus or minus go to the right hand side, minus r plus pi will be cancelled, which is equals to minus r plus 1. Theta min is equals to, then what is the value of theta here? Plus or minus pi. But just to observe, in the previous case we got the maximum direction in this same angle. Plus or minus pi is the theta max. Here what we get is the plus or minus pi is for theta min. So this case will be neglected, and this is not at all a suitable case. Just you ignore this case. Then go to the second case. In the second case, that what we have, this pi cos theta min is equals to, this is plus or minus pi, this is plus or minus pi, both will be cancelled, which is equals to 0. Therefore directly you can write theta min is equals to either pi by 2 or 3 pi by 2. So if you substitute theta mean is equals to pi by 2, you will get 0, 3 pi by 2 you will get 0. So the minimum radiation pattern will be obtained in these two directions. That what you are supposed to remember. Now once recollect what are the maximum directions. The maximum directions are along 0 and 180. The minimum directions are along 90 degrees and 270 degrees. With the help of these four angles you can draw the radiation pattern again. So what I do is just I will draw the radiation pattern. Now for drawing the radiation pattern, once again same, consider our array axis at theta is equals to 0. That is at theta is equals to 0. This is theta equals to 0 line. So this is our array axis. These are the two elements that what I am considering with space lambda by 2. And this is theta equals to 90 degrees, 180 degrees, and this is our 270 degrees line. Now as per our fresh analysis in the second case, what we got? In the direction of theta is equals to 0, we got maximum radiation. In the direction of theta is equals to 180 degrees, we got maximum radiation. So the maximum radiation will be obtained in the direction of theta equals to 0 and theta equals to 180. And what is the null direction? Null direction means the 0 radiation direction. Along theta equals to 90 degrees, 0 radiation will be there. Along theta is equals to 270 degrees, the radiation is 0. So simply what you can say is this is an end-fire array. What is an end-fire array? End-fire array is nothing but an array which has the radiation pattern in parallel with the array axis. If the radiation pattern is along the radiation array axis, then simply it is nothing but end-fire array. That's why I will name this one as end-fire array. Now to obtain this end-fire array, what are the conditions? So initial conditions what we took. The magnitude that what I applied is same, E0. Magnitude is same, but the phase difference is 180 degrees. So alpha is equals to plus or minus pi. So if I apply E0 here, I have to apply minus E0 here. The magnitude is same, but they are 180 degrees out of phase. And what will be the distance between them? The distance between them is lambda by 2. So this particular case will give us end-fire array. Like this, we can analyze these cases by considering different elements and different distances between them, and with different amplitudes and different phases. You can increase number of elements to 4, you can increase number of elements to 8. Like that you can consider any number of elements and you can vary the distance between them, and you can go for the analysis of all those things. So this is a simple introduction about our end-fire array, broadside array, and an n-element array with different conditions. Now we will discuss about a special array called as binomial array. So what is the major application of array? The major application or the need for array is to increase the directivity or gain. So in a particular direction we require the maximum radiation. Then what about the remaining all directions? We require 0 radiation. We don't want any lobe in those particular directions. But if we are considering the general arrays, we will get minor lobes in all those directions. If you go for analysis, definitely you will get minor lobes in all those directions. They are not at all required. To avoid or to eliminate the minor lobes, one special type of array is there, that is called as a binomial array. In all the previous cases, what we did, we are applying the same magnitude. That E0 is applied to the first element, second element, third element, like that. For n elements, we are applying the same amplitude. But in the binomial array, the magnitude, the amplitude of the field will be varied, and that is according to the binomial expansion that what we have. The binomial expansion what considered is a plus b whole power n minus 1. This is the binomial expansion. The coefficients of this binomial expansion will give us the magnitudes of the fields. So which is equals to, what is this one? A power n minus 1 b power 0 plus n minus 1 by 1 factorial a power n minus 2 b power 1 plus n minus 1 into n minus 2 divided by 2 factorial a power n minus 3 b square and so on plus b power n minus 1. So this is a binomial expansion which will be useful for obtaining the magnitude or the coefficients of our all antenna elements. So for this one you will get one coefficient, for this one you will get another coefficient, third coefficient, like that n coefficients will be there. All these n coefficients will be applied as magnitudes of our n element array. So instead of remembering this one, what you do is just you can remember a Pascal triangle. Using that Pascal triangle you will get the same coefficients. What is Pascal triangle? 1 1 1 1 1 plus 1 2 1 1 3 3 1 2 plus 1 3 2 plus 1 3. Like that you can write down this Pascal triangle. Now for a 2-element array, what are the magnitudes you are supposed to apply? These are the magnitudes you are supposed to apply, that is E naught and E naught. For the 2 elements, you are supposed to consider E naught and E naught. If you are considering a 4-element array, for a 4-element array, what are the magnitude ratios? The magnitude ratios are these values, that is E naught, 3E naught, 3E naught and E naught. Like that, what we are doing is just we are applying different magnitudes to the all elements. This particular arrangement will give us 0 back lobes and side lobes. That all the side lobes and back lobes will be almost completely eliminated with this a uniform distribution of our magnitudes. So this is called as a binomial array, which is a special case of arrays which will gives us 0 back lobes. With this one, a simple introduction of our arrays is over.